Hello, everyone, and welcome to this very special and seasonal episode of the Hyperthesis podcast, episode 64, where we will be delving into a lot of interesting topics related to the season. I'm Patrick.
I'm Pheely.
And I'm Liam.
Well, as you can hear, for the first time in a little bit, we don't have a guest on the show, but it is the holiday season. There's a lot of things that we want to discuss and kind of on topic of winter and Christmas and other such things. We are going to jump right into it with our intro topic, and that will be finding Christmas spirit scientifically. So this was a funny little article that came up not too long ago, but it's a kind of medical / psychological study that was published in the National Library of Medicine, which is part of the PubMed network, I believe. But it was originally published in 2015 on the 16th of December. And it's a paper titled Evidence of a Christmas Spirit Network in the Brain, Functional MRI Study. So, before we delve into the exact specifics of what they were studying to try and find the Christmas spirit, I think papers like these are excellent because they follow the scientific method, they do their research properly, but they're a funny topic to begin with. But some of the results are actually interesting. And something that I would like to discuss in a future episode is the Ig Nobel Prize. And I'm sure we've mentioned it in the past. But the Ig Nobel Prize is, instead of awarding these astounding, breathtaking, groundbreaking research achievements in different areas, it takes things that are unique or funny or very out there. And I think that area of science should be commended more because, one, it keeps people interested in it and it makes things interesting. And it's also very brave for serious researchers to say, okay, let's see what we can discover, whether it's making frogs hover, which had very serious implications for different types of things, or looking for the evidence of Christmas spirit. And while this hasn't won an Ig Nobel Prize, I don't believe, it's still a fun study, but it could have further ramifications, even though it's pretty lighthearted. So, to start, the total objective of this paper is to detect and localize the Christmas spirit in the human brain.
Could you just lump Christmas spirit in with, like, happiness or something? I guess it depends. Maybe you're one of those people who gets really stressed out during Christmas, so Christmas spirit is like anxiety. I don't know.
Well, from what I read from the article, it's more like, let's say you put someone in the MRI machine and show them like images for that related to Christmas and such, and to identify if there's anything unique about recognition or like what we so called the Christmas spirit, if I get that correctly.
All right. I'm interested to hear this from Patrick.
Yeah, so what they did was this took place in Denmark, and so they used a functional MRI or magnetic resonance imaging machine, which is able to scan the brain kind of live. So it scans over time and is able to take different readings, especially of the brain. Actually, I was in an fMRI for a study a couple weeks ago, and it was very interesting. But what they did was they took 10 healthy people from the Copenhagen area who routinely celebrated Christmas, and then they took 10 healthy people living in the same area that didn't have Christmas traditions. So this isn't too big of a sample size, but for something like an fMRI, where there's a lot of expenses and it takes a lot of time, this is pretty reasonable.
But you think they get more sample size before publishing? I don't know. It feels weird to only have 20 people in your sample size. That's nothing.
I mean, for studies like this, from what I understand, you take who you can get, and you don't always get enough volunteers. Plus, it seems like a pretty novel and, like I said before, kind of out there approach. So trying to convince people and get funding, especially for running an fMRI for hundreds of people, would be very probably unachievable.
Yeah, I guess that makes sense. There's got to be a better way to do it. I don't know. It just feels like if you're publishing something with such a low sample size, you can't accurately, you can't say like, oh, here's our results and this is what they mean, because these 20 people could be like outliers compared to, the whole population of that country, let alone the planet. I don't know. I don't like it, but all right, fair enough. Money is always a problem.
Yes. And I from the studies I've taken part in, that's more common than you think with just having low sample numbers, because getting people to volunteer their time can be difficult. But anyways, going back to the methods that they use, so they're using this fMRI machine, and what they're doing is taking scans of the brain and specifically looking at blood oxygen level dependent response. So that means that areas of the brain that receive more oxygen are most likely doing more work, aka thinking or doing some sort of processes. So they can look where oxygen in the blood is going to which regions of the brain and say, okay, this area of the brain is activated because it's consuming more oxygen. So there's a larger supply of oxygen. So what they did was these brain activations were scanned and they were analyzed for Christmas related activation in the Christmas and non Christmas groups individually. So this is what's known as a single blinded cross cultural reference. And so what they did was they essentially showed images related to Christmas to all 20 people. And then they showed similar images that weren't Christmas related to all 20 people. And they scanned their brains, saw correlations between the different images that people saw and whether they celebrated Christmas or not. So the results were that there was a increase in blood oxygen levels in the sensory motor cortex, the premotor and primary motor cortex, and the parietal lobule, which are different areas of the brain. And for people who celebrate Christmas, there were positive associations compared with scans in the group having no Christmas traditions and neutral associations. So these cerebral areas, in essence, were activated when people who celebrated Christmas saw images related to Christmas. And these areas of the brain that were activated have also been associated with spirituality, somatic senses, and also recognition of facial emotions, among other functions. So again, that's kind of where it delves deeper, and this is showing that, okay, it's not necessarily Christmas itself, but it's somewhere in the brain that activates when people think of Christmas and see images of Christmas. And there's a lot of other things going on there.
Well, I wonder because if it's what they mean by the spirit of Christmas, are they talking about in a religious context or more like a cultural context, right? Because well, from what I can roughly see, is more like cultural and traditional concept in rather than religious concept. Because you could argue that, let's say, oh, what are the images of Christmas? Usually, is a nativity scene about Christ, and I don't think that's what they're putting out as much because is it activation or more like religious belief in the brain that like when they say spirituality on Christmas? Because I think it's different. It's very different because a lot of places celebrate Christmas. They're not necessarily Christian.
Actually, they provided some example pictures within the paper. So, as an example picture, one is just a street. It's a plain street in Copenhagen or Denmark, just with cars parked on the side, some buildings along either side. And then the one beside it is another street, but it has Christmas lights strung up around it. Another example image that they have is just a bowl full of what looks like kind of cookies or biscotti, whereas the one beside it is again, a pastry kind of thing, but it's decorated to be shaped like a holly plant. So from here, it looks like there's not so much an association with religion, at least from what I can tell, and more so just Christmas decorating, or items or sites that are associated with Christmas. So they could have put a nativity scene. I know that there is a lot of religion in Denmark, but it doesn't go too into the specifics of that.
Yeah, because I wonder if that works the same way, because then one could argue that there's not spirituality, right? Because then maybe I could do it the same way to Halloween or other festivities that very nostalgic to people. I wonder if they comment on that.
They do indeed. So in their conclusions, they say that there is a Christmas spirit network within the human brain, and that this network was significantly more activated in people who celebrate with Christmas with positive associations. And they state at the very end that further research is necessary to understand this and other potential holiday circuits within the brain. And although merry and intriguing, these findings should be interpreted with caution. So they definitely say that the door is open for more research, but again, I'm sure trying to even fund this research was difficult.
Well, I think what they kind of say, what like is they're kind of making like generic argument of the holiday spirit instead of specifically Christmas, but because Christmas is such a important event that it's almost like a cornerstone of all holidays in the West, right? Then it becomes synonymous with holidays.
Yeah, and something to note is that this does take place in Denmark, which has a different culture than what we're used to in Canada. So, for example, they may not celebrate Halloween, but Christmas is pretty universal, at least in countries that are largely Christian, whereas other holidays maybe not so much.
So would Christmas spirit be unique, or would your brain have like a Halloween spirit network and a Groundhog Day network and any other holiday you can think of, a birthday network? I don't know.
I mean, again, get a few tens of people together and an fMRI and test it yourself.
I bet
But,
I would do it for free just because I'm interested. I guess I couldn't fly to Denmark, but like if I lived there and someone said you want to do this, it'll take up, a couple days of your life, I'd say sure.
Yeah, I wonder what people think about. Hey, let us take images of slices of your brain. I was like, well, I can
No,
see why some people will be like, well, maybe I don't want to see what's inside.
no, I want to know. I want to know what's in my brain. I am my brain. I want to see myself.
So, having just done an fMRI study and taking part in it, it's really interesting because you don't get to know what your brain looks like. Of course, the warning that they put is that if you have a significant malignant or some sort of growth in your brain, they will let you know. But otherwise, you don't see the data. It's completely anonymized. And you essentially just go in the tube for an hour. You do a lot of like different testing beforehand and while in the tube. But then it's done and you hope that you hear back with the published result. But yeah, it's kind of strange because it's very secretive, but also you don't know much about the study until after they've done all the data taking.
Yeah, I guess it's good that if there's any problems, they let you know. So it's like kind of a free way to get your brain tested. But also, I understand why people might not want to do it when I think about it more, because MRIs are kind of jarring. They're very loud. They're kind of uncomfortable. You're in this really tight area and you have to sit there motionless for a long time. So I guess that's definitely a negative aspect where people might say, I don't really want to do that.
Well, it's actually I don't know the medical term, but when you look for something that, well, you don't know what to look for, right? And like, let's say this is something wrong with you, but like if you don't have any symptoms, they don't know what to look for. It's actually a bad thing because they might find something that's not there because they don't know what they're looking for and say that something is wrong. And you could spend a lot of time and resources try to fix the thing that didn't exist. Might be some blob in the MRI that actually didn't exist. So it's actually better to go to the doctor when something is wrong rather than, well, I mean, there's a, let's say, annual health check that's different, right? But like if you say you have an MRI and that you are a healthy person, it's actually bad to look for something that you have no idea because it could be anything. Anything could be wrong with that images. So I suggest just, unless something is terribly wrong, then you
That's a
should
good,
be fine.
yeah, that's a good point actually.
I will point out pre-screening for things and getting screened for things is important though, because there are things that you do not feel at all, but then will come up and take you out. So especially if you're male, get screened for prostate cancer, and if you're female or have breasts, get screened for breast cancer, because both can sneak up on you and neither are fun.
Yeah, exactly. But that's like, you're looking for breast cancer and then you try to find breast cancer. But this like you're not looking for anything. You just do research and someone look at your MRI, it's like maybe there's something wrong. Then that's different. So,
but anyway, yeah, that is an interesting article, and I'm sure we'll have some more fun articles in the future. But moving on to our main topic, keeping on with the theme of the season, we will be talking about the physics of snowflakes.
Yes, I will be. And maybe you. And Pheely too. Who knows? Yeah, so this is something I was going to talk about last year, but so last year we didn't do quite a full Christmas episode, but we talked about the physics of Santa Claus, I believe. And I wanted to talk about the physics of snowflakes, but I decided I would hold off on it and save it for this year, I guess. So there's this very good Veritasium video on YouTube, which is, I feel like half of my content that I talk about comes from Veritasium or PBS Spacetime. So I when Christmas comes around every year, I think about the snowflake video because kind of snow and Christmas are synonymous, at least in Canada. And at least maybe when I was a kid before global warming really kicked off. Seems to be less so every year, but we'll continue anyway. So I watched this video last night, and basically everything I'm going to talk about is just talked about in the video. So I'm going to try and do it some justice, but I highly recommend watching it. So the first close-up image of a snowflake was taken in 1885 by Wilson Bentley, who was an American meteorologist. And in fact, he actually took over 5,000 photos of snowflakes. And he was the first to propose the idea that no two snowflakes are alike, because this guy sat there and he looked at all these snowflakes coming down and he could not find two that looked the same, or maybe they looked a little similar, but they were different. They had some different patterns on them. So he proposed this idea and he published a book titled Snow Crystals with some of these images. And this book's actually still in print today. So that's how nice these images were. There's other books with snowflakes that you can buy, but this one's still in print, so it's a good book apparently. I have to look into it. But even though he took 5,000 photos of different snowflakes, he must have looked at a very, very, very large amount of them, because out of every 1 million snowflakes or so that reaches the Earth, the surface of the Earth, only one of those might be considered in good enough condition for you to take a photo of. So when you imagine like a stereotypical snowflake, like if you ever watched the movie Frozen, or you're watching some Christmas holiday special and it shows a snowflake falling down from the sky, it's this very like pristine, flat, two-dimensional ice crystal. Only one out of every 1 million or so of those looks like that. The rest have been very heavily damaged on their way down.
Well, when I first came here, I had in my head the snow is gonna fall down. Looks like the snowflake that I saw on TV, and everything was just this little white blob that fell down from the sky. I was scammed. I was like, this wasn't as magical as the movies.
Yeah, and it's less magical when it's flying sideways at you as well, and there's cars screeching around and sliding across the road. People are falling on the ice. But still, snow can be magical. But yes, maybe only 1 out of every 1 million snowflakes is magical. And so as these snowflakes fall to Earth, I'll get into how they form a little bit. But before that, as these snowflakes, you can imagine that you get some pristine snowflake formed up in the atmosphere, and it's falling. They collide with each other. They change pressure and temperature, and the edges of them melt a bit, and the wind kind of can break them, and all kinds of things. So by the time they hit the ground, they're this like deformed blob of crystal that's maybe it's a bunch of them clumped together as well. You can get these really big clumps of snowflakes, like you said, these balls. So if you want to find a really nice snowflake, it's harder than just looking at the first one that lands on your hand. You have to sort through them, and I think that's what this guy did. He'd have this big thing, and all the snowflakes would land on it, and he'd look at them, and then he'd kind of like swipe them away, and he'd say, all right, there's none here, and I'll wait for some more, and eventually he might find one if he's lucky. So take 5,000 and multiply it by, I don't know, 1 million, and that's probably how many snowflakes he looked through. Probably more, but that's a safe bet for a minimum amount. So there's a lot of questions regarding snowflakes that this guy had, I'm sure. And we understand them way better now today. Our understanding of snowflakes is actually largely thanks to one physicist and maybe this people. It's like any physics collaboration, right? One person tends to get most of the credit and other people's names don't get recognized. So there's probably more, but this is the guy who kind of led the operation, Dr. Ken Libbrecht. I might be pronouncing that wrong. I apologize. But he's currently the world's leading expert on snowflakes, which is an interesting title to have, to be sure. And I'll talk about that some more later. So there's all these different mysteries he wanted to understand about snowflakes. So imagine this kind of perfect snowflake that I talked about before, like this nice snowflake you see in a movie, this two-dimensional, very pretty looking crystal. You might wonder, why do all snowflakes have six-fold radial symmetry, which is just a fancy way of saying if I take a snowflake and I rotate it 60 degrees, it looks the exact same as it just did. So why do they have this symmetry? You might wonder why no two snowflakes seem to have the same shape. Although they might look similar, they're all kind of fundamentally different a little bit. You might wonder why they're so complex, yet how are they all still different? They all form in the same place, so when they reach the Earth, why are they different? Why they're different? There's each snowflake, well, there's a bunch of them, but the pristine ideal snowflake, each of them has 6 kind of arms that come out, and why do they all form the same? How do they mirror each other so perfectly, and why are they flat? They're roughly two-dimensional. So there's all these really interesting questions you can ask about them, because they're all made of frozen water, right? They're all made of the same stuff. They're identical on a molecular structure. So how do they form different shapes? There's a ton of different questions.
Well, I like how, physicists are solid state people like to say, oh, six-fold symmetry, two-fold symmetry. But in my head, it's just like, well, it's just like, let's say it's shaped like a hexagon as a six-fold symmetry.
Mm-hmm. That's
not
what it is,
necessarily.
right?
Yeah, right. It doesn't have to be a hexagon, but I think when people say the six-fold symmetry is not really a generic term, it's kind of hard to understand when you are not in the field. Anyways, I think probably one of the similar reason, my guess would be that because the inner angle of hexagon, I think, is 120 degrees for, like, let's say when all the sides are equal, right? And the angle of the water molecules, I think, is 109 and a half, like around 100. It's close to 120. And when it's formed a crystal, it means it's formed like a lattice, which is like how do you explain a lattice? Like a repeatable set of arrangement, right? It's like a lattice is not inconceivable that those angles would form something similar to hexagon. And also, I think what we find out in science is that the microscopic structure usually manifest in macroscopic structure, like salt, right? The table salt is a simple cubic, if I remember correctly. And the macroscopic structure, which is the salt we see also forms a cube, and their smallest molecule, smallest site, or the crystal structure is also a cube. So it could be the case, or it could not be. I think there are some that the in the larger scale is look a little different, but sometimes they look really similar.
Yeah, well, your intuition is bang on. So when I said six-fold symmetry, I mean like a hexagon shape. You rotate a hexagon 60 degrees, it's a hexagon still. It looks the exact same as it did before. But also, yeah, the reason why these snowflakes form these shapes it's because of their molecular structure. It's one of these interesting cases of, like you said, table salt, for example. But I'll come to this in a bit soon. But well, I'll talk about it now. You're right. It has to do with this angle of water and the fact that a water molecule, H2O, 2 hydrogen, 1 oxygen, it looks kind of like a boomerang to me, where the center of the boomerang is your oxygen molecule and the ends of the boomerang are your hydrogen, your hydrogen atoms and oxygen atom in the middle. So it's one of these really interesting cases of the quantum mechanics that governs the microscopic behavior results in the macroscopic structure of a snowflake. And I think that's a common thing in condensed matter physics with crystals, is that you can kind of look at the shape of a crystal like table salt and you can say, oh, it must have this specific type of crystal structure going on. Sorry, my cat is a menace. So how does a snowflake form? How does this have an effect on the macroscopic structure? So all these different snowflakes, even though they all look different, they all form in kind of the same way. So in the atmosphere, you have water molecules, you have water vapor, and as these molecules jiggle around and bump around and float, some of them move up higher, and as they rise higher, they lower in temperature and they become super saturated. I'm not going to get into that too much, but basically what this means is that there's little dust particles in the atmosphere. These water molecules will all condense on these dust particles to form tiny droplets of liquid. So that's kind of like how rain forms. Maybe it is how rain forms. I forget. But yeah, okay, Patrick nodding his head. Yeah. But it turns out that if it's cold enough, the temperatures are very low, high up in the atmosphere. They can be lower than freezing. So even though these water droplets are in liquid form, condensing, forming on dust particles, they're in this metastable state, which Pheely used to research. This supercooled water is what it's called. So it's liquid, but it's only going to be liquid for a finite amount of time until inevitably, from a single kind of small point within the water droplet, ice will start to form. And once it forms, it spreads out everywhere, and the water droplet becomes frozen, becomes ice. So all these tiny little condensed droplets will turn into ice crystals on their dust particles. And when this happens, the molecules that make up the water begin to align with one another to form this hexagonal crystal lattice of ice, which is what we Pheely mentioned. And this is all because H2O, water, it has a very unique molecular structure. It has this bent boomerang shape that I talked about. You can imagine this oxygen molecule, and then sticking out from it are two kind of branches. Each one has a hydrogen molecule, and there's this 109.5 degree angle between the two hydrogen atoms, roughly. I think it's a slightly more precise number, but that's close enough. And because of this, it has polarity. So one end, because the hydrogen atoms have an electric charge and the oxygen atom has a different electric charge, and because it's bent, one water molecule will have a polarity. One end of it will be slightly more negatively charged, and one end will be slightly more positively charged, electrically charged, not to be confused with magnetically. So if you have all these different water molecules, they're all next to each other, and they all have positive and negative charges, and we know that like charges repel and opposite charges attract, so they all kind of link together, and because of where the polarity is on the molecules, they form hexagons, and they periodically form all these repeating hexagons of water molecules that link together. So that's your hexagonal crystal lattice, and that's where they get their macroscopic shape from. So after the water freezes and the molecules, oh, sorry, Patrick.
Oh, I was just going to say, it might be interesting at this point just to mention that ice doesn't have to be hexagonal. This happens under atmospheric conditions and pressure, but I think there are something like 10 or 11 different forms of ice.
Like more than
something
16, something ridiculous.
Yeah, there's a whole bunch of different ice that forms in different temperatures and pressures. And this is something that an old professor of ours, Dr. Peter Poole, studied. And some of us here have worked with Peter. And there's a lot of interesting things about ice that can be said, but hexagonal ice is pretty cool.
I think we might have talked about that. So in that atmospheric optics episode, because I like atmospheric optics, the kind of nice rainbow looking things you see in the sky are, a lot of them are from ice crystals that form, and depending on the shape of the ice and what its crystal structure is, you see different types of rainbows in the sky, right? So I talked about that. So like some of them are flat hexagons, some of them are long hexagons, some of them are like these weird diamond shapes. There's a bunch of different kind of crystal structures you can get. But snowflakes are particularly these hexagonal crystal structures. And I also talked about how there's this like rare form of cubic ice that people weren't sure about existing, but some researchers were claiming they found it naturally in nature or they created it in a lab. I don't really remember, honestly, but I know I've talked about it before. So yeah, there's a whole bunch of interesting things. Water is a very, very, very interesting molecule. It's very special. I mean, we're alive because of it. There's so many things that it does that are unique. So we could talk about water for days, honestly.
Yeah, there's something special about that molecules angle. I think I talked about it before, right? That water is also one of the most anomalous material in the universe. Doesn't behave as we expect, and it's very interesting how this specific type of molecules, it's not just water. Like I think silicon dioxide has a similar anomaly to the fact that the molecule has this strange angle, contributes to their anomalous properties. And when you say we are here because of that, it's kind of true, and also kind of like I think it's the opposite. It's because of that is why we are here.
Yeah, I just know that if I didn't consume any water for a day or two, I think I'd die. So I'm definitely here because of water. I don't know about you, but
I think it's 3 days without water.
Yeah, it's not
depending on.
It's not very long. You can go a long time without food, but without water, you will die very fast. But anyway, so you get these little ice crystals, these little hexagonal lattices that form up in the atmosphere. So how does this become a snowflake? Right now, it's just a little kind of ugly blob of hexagonal ice. It's not even macroscopically, it's not even a perfect hexagon yet. So if you zoom in close enough, you have a hexagonal lattice. But if you zoom out, it's this little kind of ball / deformed blob of ice. So after the water freezes, more and more water molecules floating around the atmosphere, they'll bump into this little chunk of ice, the kind of seed for our snowflake. And as they do, they'll attach to it. Some of them will bounce off, some of them will attach to it. And the flatter the surface is, so you can imagine that you have the edge of this if you zoom in on the edge of this little chunk of ice, it'll be all deformed and bumpy, made out of different water molecules. But if they hit a particularly flat region, there's a higher probability that the water bounces off. And if they hit a really deformed region, there's a higher probability that they attach to it. And I think this is thermodynamic reasons. You can do entropy calculations and calculate probabilities of this. It minimizes the energy. I think there's energy reasons and entropy reasons why this happens, but it's kind of like a statistical thing. So what ends up happening is that all the deformed regions get more molecules attaching to them, so they become flatter. They become flatter faster than the water molecules can attach to the already flat regions. And after enough time passes and enough water molecules start attaching to this little chunk of ice, it actually expands out and the edges become flatter and flatter and flatter until eventually it looks like a perfect hexagon. It has 6 very flat sides and 6 points. So it actually will, for this hexagonal lattice will form macroscopically a hexagon made out of many, many, many different water molecules. So this is what I find super cool about it. You have microscopic hexagonal structure, which forms a macroscopically large hexagon, which is the beginning of your snowflake. And I think there's another talk on YouTube that this guy, Dr. Ken Libbrecht, again, maybe I pronounced that wrong, but there's another talk on YouTube that he gave at Perimeter Institute, which is close to where I am. And the whole reason he got into studying snowflakes wasn't because it wasn't because he was just interested in them at first. He didn't just look up in the sky and say, I'm going to study snowflakes one day. He was studying actual like different types of crystals, different types of solid state systems. And he wanted to understand why the kind of macroscopic structure of these crystals looked the way it did based on the microscopic properties. He wanted to better understand that. And when you study, if you're in a lab, in a physics lab, and you want to study these specific certain types of crystals, it turns out that a lot of them are very expensive. They take a long time to get to you. Sometimes they only crystallize under very extreme temperatures, very hot or very cold, usually very cold. Sometimes they're toxic or poisonous, so you have to go through all these extreme measures to study them. And he kind of figured, well, snowflakes are a crystal. I can just use literal tap water to make them, and I only need to go anywhere from 0 to negative 40 degrees Celsius to create them. So, and it's not like I have to do any of this toxic poison stuff to make sure they don't hurt me. I can just pour once my experiment's done, I can just pour the melted water down the drain. So it was kind of like this ideal, very practical way to study crystal structure, and I think that's where he started getting into it from.
Well, I mean the tap water depend on where you are too, right? It has a lot of contaminants per se to keep it safe for human. I think chlorine is one of the substances used to make sure the water is not contaminated, right? But it's just a slight amount. It's not like in the pool where there's a lot of chlorine. You know, when you eat or accidentally drink water from the pool when you swim, it's like it tastes janky. You can smell the chlorine, especially when they just put more in. I think tap water depends on the place to have a distinct taste too, and those contaminants may obstruct the crystallines forming, and that's why I think when you do research, they actually have to get like some water that's representative of the atmospheric water.
Yeah, getting rid of all the impurities, I think, is just way easier than dealing with all the other stuff I said if you want to study other crystals. I think it's I know chemists do this all the time. You take water and you can just, is it called distilled water when you get rid of all the impurities?
You just distilled it. Yeah.
Yeah.
Well, I mean,
yeah.
Or deionized water.
Deionized, that's right.
Yeah. Also, deionized. I think it's more than distilled, right? Distilled because there are also other substances that evaporate and they come along with the distillation process.
Yeah. So getting
there's a complex process that involves like 3 or 4 different types of filters, including like a UV light and a whole bunch of things. But properly deionized water, which is a little bit different than distilled water, has like it's measured in purity based on resistance, and it's something like 18.2 mega ohms of resistance will be perfectly deionized water.
And I think even like in the atmosphere, there's a bunch of other gases floating around, even and snowflakes still form. So maybe you don't even need to really, maybe when you get this water, you don't even need to perfectly kind of purify it. There can still be probably trace amounts of things and you're fine. That's my guess. But anyway, so kind of the final journey that the snowflake takes. So now it's in the sky, it's formed, it's created this kind of hexagon, but how does it get these really intricate kind of arms that come out of it? So what happens is that because of what I said before, because molecules are more likely to bounce off flat surfaces, you can just imagine a hexagon made out of ice. More water molecules are going to attach to this thing, but they're more likely to attach to the 6 points of the hexagon. So you get these 6 kind of like long arms that come out of the hexagon. So you get 1 per point, and they begin extending as more water molecules attach, and they have their own kind of deformations on them. So you can get little like pointy bits that stick out of these arms, and that's kind of what ends up as time goes on. The snowflake will grow and grow, and you get this six-fold symmetry. You get these six kind of very nice looking arms that come out, and you get your very, very nice looking snowflake if all goes well.
Well, it makes sense though, because like why we attach to the flat part? Because if you imagine bunch of hexagons, right? Like not just one, and you want to attach them together into the lattice, it's like you kind of have to grow it from the edges. Sorry, not the edges, the corners, right? If you want to grow that, you grow it from the corner, because if you grow it from the side, there's nowhere to go. It's already a side of another hexagon, so you have to grow it from the corner.
Yeah, I think to a physicist it's very intuitive, but I'm trying to get that point across, because if you're listening and you're not a physicist, I'm not sure how intuitive this is to you, because I know like in all the like if you explain this to a physicist, there's very many reasons I think why it makes sense to them, because you've seen similar things happening in all these different physics courses I've took, and it makes sense. But yeah, so that's how you get kind of this ideal, very nice looking movie snowflake. But it turns out there's all kinds of different snowflakes. So one snowflake can be formed out of roughly 100,000 droplets of water, and each droplet of water is many, many, many different water molecules. And Dr. Libbrecht took it upon himself to kind of understand this forming process, so he researched that a lot. And he was able to identify that there are over 35 types or kind of primary families of snowflakes that can form under different conditions. And some of them look nothing like these very beautiful two-dimensional snowflakes. So he found that you can get hexagonal columns that form. So there's all these. I'm not going to list all 35 of these families, because each of these families can probably be subdivided into even more specific things. But you can get hexagonal columns that form. So you can imagine like a big long hexagonal pillar, kind of. You can get these long needle-like flakes. You can get the columns that are hollow, and combinations of these. So you can imagine that you can get like long columns, but then the ends of them become flat, and all kinds of stuff. And it all depends on the conditions they experience as they fall from the atmosphere to the Earth. So in a sense, you can kind of look at a snowflake and you can kind of reverse engineer it in your head and determine what conditions it fell through when it reached the Earth. So you could say, you can imagine that, all right, you have your little ice crystal and it forms a column. So you have this very really tall, long hexagon shape, but then at the end of it, two flat plates form on either side. So you can say, okay, so as it started falling, there were these specific humidity and pressure conditions, so it formed the column. But then as it got closer to the Earth, those conditions changed and it started moving out on its edges. It kind of like flattened off. So it's you can kind of, I guess, if you know a lot about snowflakes, you could catch one in your hand. If you have really good eyes, you could look at it. Usually you need some kind of magnifying glass or a microscope, but sometimes you get really big, nice looking snowflakes. You could look at it and you could actually tell what kind of conditions are happening in the clouds above. This explains actually why snowflakes are extremely intricate and why no two snowflakes looks the same. It's because every single snowflake takes a slightly different path than every other snowflake as it falls. And details as minute as how close two snowflakes were together as they fell can affect how they form. You can imagine I have two of these really nice, beautiful looking snowflakes, these two-dimensional, these movie snowflakes I'm calling them. If two of them are falling and they get too close to each other, they now have to compete over water molecules in that region where they're close to each other. So the regions of them that are close to each other don't grow as much as the rest of them do, because they're fighting to eat up water molecules. So now these two snowflakes aren't symmetric anymore, and then they can do other things as they fall, like wind and bump into each other and stuff. So there's so many things that can cause them to look different. One snowflake might be in a different region with slightly more humidity, or one of them might be too close to other snowflakes, or one of them might be hit by the sun on one side more than another one is as it falls. By the time they hit the Earth, they're all very, very different. And how Dr. Libbrecht was able to actually figure this out is he created a device in his lab where he could create as near perfect as you can get snowflakes using this super cooled water and dust kind of method. And he could directly manipulate the conditions that these snowflakes exist in and kind of make custom made snowflakes. I think he calls them designer snowflakes. So he could start off with his little ice crystal. He's like, all right, I want it to start off as a nice 2D hexagon. So he'd ramp up some voltage in some machine, and that would cause it to grow out as a hexagon. And then he says, all right, now we're going to stop this, and we're going to make these really, really long arms. And he would crank some other knob, and that would cause the arms to grow out. And then he says, all right, I want it to have points on the end, and he would turn some knob and do that. So this Veritasium video is super cool. You can see him like custom make these snowflakes and create them in an ideal setting where they don't have to pass through all the complex stuff happening in the atmosphere. And that's why his snowflakes were actually used in the movie Frozen. He was the snowflake consultant. So all the snowflakes in that movie were ones he's created in his lab and they took pictures of. Even there's lots of postage stamps throughout the world that are snowflakes. I think most of those are his. The postage companies contacted him and said, we want nice photos of snowflakes for our postal stamps. Can you provide us with some? And he did. So it's kind of an interesting, it's not something that happens a lot to physicists where they get involved with the real world like directly. It happens, but some physicists it's more common for than others. So with this device he created where he can make kind of any snowflake he wants, give it the certain conditions to form it the way he wants to, he was able to kind of develop this grand unified theory of snowflakes, which matched the experimental data that he got. And he was finally able to understand these intricate details about how different conditions cause different snowflakes to form. So the particle physicists out there kind of need to up their game, their grand unified theory game, because this guy came up with a grand unified theory of snowflakes before they could do their grand unified theory of particle physics. Dr. Libbrecht also has many different books that he's published with very nice photos of these snowflakes and descriptions of them. And interestingly, so I said he started off doing research surrounding the reason why he got into snowflakes is because he was doing kind of more crystal structure stuff with kind of solid crystals, not these snowflakes. But he also conducted research in all these different other areas of physics. I was looking at his Google Scholar page, and he's done like experimental laser physics. He's done a lot of gravitational wave physics and written papers on LIGO. He's done astrophysics papers and the physics of the sun. So he's got kind of one of these very broad backgrounds of different areas of physics under his belt, which that's something kind of I want to do. I very much like that. So I'm taking inspiration from him.
Well, thank you for that chilling topic, we'll say. It was very interesting to learn about snowflakes and how they're formed. So to end off this episode, we are keeping on the theme again, and we will be hearing a story from Pheely about some teleportation and Christmas.
Patrick, how can people reach us first?
Oh, well, I guess that's important. People can reach us many different ways. If you would like to reach out to us and contact us, we have an email. We are hyperthesispodcast@gmail.com, where you can send us an email with questions, comments, or if you are an expert in your area, we would love to hear from you. We especially love having graduate students or students on the show because they're always doing interesting work, and we've had a string of guests on. So if you want to contact us through email, you can do it at hyperthesispodcast@gmail.com. We also have Instagram. We're at the Hyperthesis, where you can find updates about when we are posting episodes, along with teasers about what those episodes are about. You can also find information, especially when we take breaks, of when we'll be back. We occasionally post memes on there. There's a lot of good stuff on the Instagram, and you can send us a DM as well. If you are trying to listen to us, we are based in many, many different podcasting services, whether it's Apple Podcast, Google Podcast, which is being shut down, Audible, along with many, many other podcasting services. So wherever you get your podcast, you can find us, you can share us. Feel free to give us a rating, subscribe to us. We are always interested in spreading our episodes. Finally, we are on YouTube. We are pretty well up to date with our episodes. I believe we just uploaded episode 61 at the time of recording. So Pheely's doing an excellent job keeping up with that with this new MacBook, which is lightning fast with processing. We are not sponsored by them. Don't get a MacBook if you don't want it. But you can find us on YouTube, so feel free to subscribe, leave a comment, leave a like, and reach out to us any way that you prefer and share our episodes. So now, finally, we will hear a story from Pheely, keeping on the theme about Christmas quantum teleportation.
So this was what Liam told me about this paper that he found on this very popular preprint website, the archive. If you know, you know. If you're in scientific publication, the archive is the
goat.
the mecca of preprint. And so usually by the holidays, there's always a bunch of papers on some funny things about the holiday. And it's really nice that to see sometimes. So this one is about quantum teleportation, but they use Christmas story to try to explain or propagate the information about quantum teleportation. So the story is not exactly a story. I don't want to just take their story and tell it. So I'm gonna do a quick. I'll explain what the paper kind of talks about. So this one is from the Dutch physicist. Maybe he's not Dutch, but it's in Eindhoven University of Technology in the Netherlands. So by Barry Fitzgerald. So it's basically try to explain quantum teleportation using Christmas terms. So basically, instead of let's go use the classic Alice and Bob transfer of information, is the Santa Claus sending presents to the children around the world. And how can he solve that problem using quantum teleportation? So in this sense, it's actually they're not physically teleporting the gift. The actual teleportation is actually in the information part. So the premise is that the Santa Claus want to send books to all the children. Like books, all right. Who read books anymore? Anyways, I know a lot of people read books. I still do. We all do. But children. So there are two types of book. One is gibberish. The other one is the one that they want. And so there's like two states, right? Gibberish and good books. And they're gonna use that to use quantum information or quantum teleportation to transfer whether the book is gonna be gibberish or not on the day of Christmas, on Christmas morning. So essentially, what would happen is that in the North Pole there would be like a entanglement machine where there gonna be two books that got put in the machine, or could be even more. But there'll be books that are entangled through the machine. We call this the quantum entanglement. And what's special about quantum entanglement is that when things are entangled, it's like they're connected in the quantum way. So, well, what that means gonna manifest in a minute. So when books are entangled, you can determine the state of another book with the book you with what you can determine the state of one book with another book. So what happened is that we go through this Christmas entanglement machine to have these books, and then the elf would go deliver it on, let's say, Christmas Eve, and Santa get all this entangled book with the content is like this superposition of content. So it can either be gibberish or it can either be the good books. However, if it's opened before is measured in the entanglement machine, it's always become gibberish. So it's like Santa have the key basically. It's like you deliver all the books to the children, but they don't have the key. So if you don't measure it in a specific way, it always turns out to be the gibberish. And then the Christmas morning comes around after Santa the elf deliver all the books. Santa come back to entanglement machine with the ledger, with the good nature ledger, so see who's good or bad, and then measure the state of the another entangled book that Santa have, and that would transfer information, basically almost like teleported to the books that the children have. So children can either have good ones, the one that they want, if they behave well, and the ledger said, well, send them the correct measure using the correct key, which would instantaneously, hopefully, change the state of the book in the children's home to be the one they want. Or if the ledger say, hey, you're a naughty kid today or this year, the book would turn into gibberish. So you would have a gibberish book in your house. And that's the way they incorporate quantum teleportation. So as you may notice, the Santa still has to do the actual delivering of the physical book to the children's home, but the actual teleportation comes into play for the information part. And that's how quantum mechanics, the quantum teleportation work is usually on the information, not the what do you say, quantum teleportation is not a physical thing that's got teleported. And it is a teleportation because it's a transfer of information. Santa actually lost the good book information in the North Pole is actually being transferred to the book on the in the children's home. So it's actually a transfer of information, not a copy of the information. So what they do here is basically create this analogy using Christmas terms, and a little more complicated, right? Because now it's about books and delivery system, but essentially it's a story of that describe the nature of quantum mechanics and how we can use that or utilize that to transfer information. I think it has an implication on quantum encryption too. How do you transfer information securely? Because if other people don't know how to measure it, or even the receiver, if the Santa doesn't go to the entanglement machine and measure their side, their state a specific way, the children would always get gibberish. And I think compared to the real world, if you want to send information to someone securely, you don't want anyone to open it and understand what it is. So maybe we could do specific way of entanglement that only when we measure it a certain way, only when we know we get the correct person or correct receiver, we can collapse the wave function in such a way that the correct information is transferred. It's like having a key that you have in your machine, but once you turn the key, the receiver would instantaneously get the correct information. Well, I mean, I don't think it's instantaneous, but you have to send basically what you measure, the state you measured, to the other person, so they can, correct their state to get the correct information. So that's the story that they came up with for the Christmas and teleportation.
I feel like that might, I don't know, a little convoluted, I think, but quantum entanglement is a tricky subject, so maybe that's a good way to teach it. I don't know, but maybe, you know what, Santa, he has to deliver the book anyway, right? So what he could do is he could deliver the book, but then each year for Christmas, he only gives them one page. So that way he only has to deliver the book one time in their life, and then by the time they're older, they've got like a full book.
No, because every time and then every year you have to go back take the page back and re-entangle it in the machine.
No, but you do one page 1 year. So each page is separately entangled. So you do one page 1 year, and then the next page the next year, and so on. So that way you only have to deliver the book once. You don't have to like bring it back and forth every year, right?
Imagine being able to read one page every year. It must be some good book, because like, or you have to wait 1 year to get the next leaf or
Yep.
page.
Exactly. And maybe it's
it's
not
kinda hard.
yeah.
Maybe because we are more used to it, like it's hard to explain quantum teleportation or quantum transfer of information or entanglement without knowing the superposition, without knowing quantum mechanics, without knowing the map, a little bit of linear algebra, right? Like to be able to understand what exactly is going on. So I'm not sure how effective a story would be in try to paint a complete picture or a better picture, not complete. Right? It's not going to be a complete picture, but I think it's provides some analogy. I actually like the mittens more than the one we had, but it's essentially the same thing, but in a Christmas analog.
Well, with that, thank you for that very interesting story / description of the paper, Pheely. And Santa, if you are listening to this, we would like to know your secrets and how you became such a good physicist. Because truly, the fact that he can deliver billions of packages a night, which we discussed in our last episode around this time, which was episode 27, Santa's clearly either a crazy physicist or he's got some wild engineers on his team. So thank you for joining us for episode 64, this little winter / holiday themed episode. And thank you for joining us. We'll see you in the next one. Bye, everyone.
Take care.
Happy holidays, Merry Christmas, good luck shopping, Happy New Year's, whatever. See ya.